This is a sample problem on static equilibrium involving torque. In the figure, a cable supports a hanging mass 2 kg and a 5 kg bar with a length of 4 meters that is hinged to the wall. What is the tension T along the cable if it makes an angle of 30 degrees with the horizontal? So, in solving problems like this, the first thing that we need to do is to identify the forces that are acting on the object that is capable of rotating. So in this case, that object is this bar right here. So we need to identify the forces that are acting on this bar. So first, we already have tension. Next, we have the weight of this hanging mass. So the weight of this hanging mass is could be represented by an arrow directed downward, and it could be solved or we could label that as Wm. Another force that is acting on the bar would be the weight of the bar itself, and the weight of the bar could be represented by an arrow directed downward and is drawn at the center of the bar. So we would locate the center of mass of this bar, right, and we could put that in the middle, and we could draw an arrow directed downward to denote the weight of the bar, or the force of gravity that is acting on the bar. And there's also another force, since the bar is attached to the wall, so the wall is going to exert a force on the bar in that direction. So we would call that Fw. Now, after we have identified the forces, we are going to assign the axis of rotation, or the pivot point. Now, the axis of rotation or the pivot point is actually an arbitrary point, so it could be anywhere along the bar, but then it is best advised that the axis of rotation will be located at the point where a force is found, or forces are found. So in this case, the following points are these. So we have this point, and we have this point. So once again, we could draw the axis of rotation at a point where the forces are. However, the problem would also help us determine which point is most appropriate as the axis of rotation. So since we are interested to solve for the tension along the cable, so meaning this tension, so meaning we cannot assign this as our pivot point, because the moment that we assign a point as a pivot point, all the forces that are acting there will result to a torque of 0, because remember that torque is equal to Fr sine theta. So meaning to say, if the force is acting on the pivot point, so the R becomes 0, and therefore the torque that is being caused by that object by that force becomes 0. So here we cannot assign this as our axis of rotation, because if we assign this as our axis of rotation, it would cancel out the torque that is caused by the tension, and therefore we will not be able to solve the problem. So remember that we are interested in tension. So now we are left with these two pivot points. Based on the problem, we can actually solve for the weight of the bar, but then there's nothing in the problem that tells us anything about the force that is exerted by the wall. So remember that if we assign a pivot point, the forces that are acting on that pivot point would result to a torque of 0. On that note, we could actually assign this as our pivot point, because the problem does not give us any information about the force that is being exerted in the wall. So therefore, if we set this as our pivot point, we no longer have to worry about the magnitude of this force. Now, this problem is about static equilibrium, and when we say static, this means to say that the torque in the counterclockwise direction is equal to the torque in the clockwise direction. So how do we know which forces would result to a counterclockwise torque and which force would result to a clockwise torque. So it has something to do with the direction of the force and the direction of the axis of rotation. For example, we have the weight of the bar. So the weight of the bar, which is directed downward, and our pivot point is on its left. So this force here would actually cause the object to rotate in the clockwise direction. So with respect to this pivot point, the force of gravity on the bar, or the weight of the bar, would cause the object to rotate in this direction. Similarly, the weight of this hanging mass would also cause the bar to rotate in that direction, so clockwise direction. And now let's look at the force or the torque that is caused by this tension. So with respect to the axis of rotation, that tension could make the bar rotate in the counterclockwise direction. So let's put that into the equation. So the torque counterclockwise would just be the torque that is being caused by tension, and that is equal to the torque counterclockwise, so meaning to say the torque caused by the weight of the bar plus the torque that is being caused by the hanging mass. Now expanding torque, so torque is equal to Fr sine theta, this is for the tension, is equal to Fr sine theta for the bar plus Fr sine theta of the hanging mass. Now Fr sine theta for the tension, so the F is just equal to the tension multiplied by the R. So the R is just equal to the distance between the axis of rotation and the point where the force is exerted. So if this is the axis of rotation and tension is exerted at this point, so therefore the R for the tension is the length of the bar, and that is equal to 4 meters. So let me substitute that. That's equal to 4 meters multiplied by sine theta. So the theta now is the angle between the line of action, this is the line of action, and the force. So this angle right here, and that is equal to 30 degrees as given in the problem. Now let's expand the Fr sine theta of the bar. So the force of the bar is just equal to the weight of the bar, and remember that the weight of the object is just equal to the mass of the object multiplied by acceleration due to gravity. Let me move that here. Alright. Therefore, the force of the bar is just equal to the mass of the bar, and that is 5 kilograms multiplied by acceleration due to gravity, 9.8. Now the R, once again, is the distance between the pivot point and the point where the force is being exerted. So in this case, the weight of the bar is drawn in the middle of the bar, so the R in this case is just equal to 2, because if the total length of the bar is 4, so half of it where we have drawn the weight of the bar is going to be 2 meters. So I would say 2 sine, and our angle here is 90 degrees because the weight of the bar is directed perpendicular to the bar. So the line of action is this, and then the force is directed downward, so we will have 90 degrees. Plus the Fr sine theta of the hanging mass now. So similarly, the weight of, or the force of the hanging mass is just equal to the weight of the hanging mass, and that is equal to its mass. Let me just put this in a bracket. That is equal to the mass, which is 2 kilograms multiplied by 9.8. Now the R would be the distance between the pivot point and the point where the force is exerted. So since the hanging mass is hanged at the very end of the bar, so therefore this R right here, or the distance between the point of the or where the force exerted, and the pivot point or the axis of rotation is going to be the length of the bar, and that is equal to 4 meters sine. And similarly, the weight is directed perpendicular to the line of action or the bar, then our theta is equal to 90 degrees. So now we have properly substituted our equation, and this would then allow us to solve for tension. So you could just calculate this on your own. Tension is going to be equal to 88.2 newtons.